हेलो स्टूडेंट्स एंड वेलकम टू द लेक्चर। तो जैसा कि हम सब हेलो फ्रेंड्स एंड वेलकम टू द लेक्चर। तो एज वी ऑल नो, we had started the discussion over the unit and dimensions, and previous one was our part 1. Now we are going to start the discussion over the part 2. Got it? In this lecture, basically we will cover the units of mass, units of time, units of temperature, units of electric current, units of luminous intensity, units of quantity of matter, dimensions of physical quantity, and at last we will see the summary of all of these. Okay? But before starting the lecture, as usual, we have our small disclaimer over here that we are required to understand first before we proceed. So the disclaimer is like, the images used in a slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this track and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. Now, units of mass is the thing that we are going to start over. Basically, in SI system, which is the international standard of units, mass is measured in kilogram. In 1889, 1 kilogram was defined as the mass of the cylindrical piece of platinum iridium alloy kept in International Bureau of Weight and Measures. Subunits of kilogram, the smaller units of mass in common use are gram and milligram. Okay, like we could say, whenever we have to measure the mass, okay, so to define the quantity of the mass, we usually use kilogram because kilogram is the measurement unit of mass as per the SI system. Got it? In 1889, that was happened when the cylindrical piece of platinum iridium alloy kept in the International Bureau of Weight and Measures got defined as a 1 kilogram. Apart from this kilogram, the other smaller units that we use are the gram and milligram respectively. Got it? 1 gram is equal to 10 power minus 3 kg. 1 milligram is equal to 10 power minus 6 kg equals to 10 gram minus 3 kg. Multiple units of kilogram, if we talk about, the bigger common units of mass used in daily life are quintal and metric ton. Okay, these are the bigger common units. Like you can say, kilogram is the standard units. Below it, we use gram and milligram. Above the kilogram, we use quintal and metric ton to measure the mass. 1 quintal is equal to 100 kilograms, or you can say 10 power 2 kg. 1 metric ton equals to 1000 kilogram, or you can say 10 power 3 kg. Now, further, in unit of mass, non-metric unit of mass, the mass of atomic particles such as proton, neutron, electron, these are expressed in unit called the atomic mass unit or AMU or the unified atomic mass unit. Like we could say, these are metric. These are the metric. Okay. Now we are talking about the non-metric unit. Okay. AMU or unified atomic mass unit. One atomic mass unit or U is actually the 1/12th mass of one carbon 12 atom. Okay. Now the question will be, why we only choose the carbon 12 atom? Why not any other atom? So basically, in order to find the answer, we could say, when we were defining the standards, all right, so we found out one thing: every element having the different numbers of proton, neutron, electron, and it is hard to set a standard by considering them. That's why we use carbon 12 atom, because only the carbon 12 atom having a capability of 6 proton and 6 neutrons. Okay, this is the unique number that is found with the carbon 12 atom, and that's why we use the carbon 12 atom to define the categories. One atomic mass unit or unit is equal to 1.655 into 10's power minus 27 kg. Okay, now the mass of large heavenly bodies is actually measured in terms of the solar mass. Now we are not talking about the any kind of physical body, we are talking about the heavenly body. Also we call them as space bodies and all. These space bodies larger in size, that's why it's hard to exactly measure their weight in terms of the kilograms and on the other standards. So that's why we measure them in terms of the solar mass. Okay, one solar mass equals to 2 into 10's power 30 kg. The largest practical unit of mass is Chandrasekhara limit, and one Chandrasekhara limit, which is being represented here by CSL, is actually the 1.4 times the mass of Sun. Alright. Smaller and bigger units of mass, if we consider them. So now here we have the result. Smaller mass, the value in kg. Bigger units, the value in kg. First unit, gram, 10's power minus 3 kg. Second unit, milligram, 10's power minus 6 kg. Then atomic mass unit, 1.655 into 10's power minus 27 kg. Bigger units we consider quintal, 100 kg, metric ton, 1000 kg, and solar mass, 2 into 10's power 30 kg. Because this is the Chandrasekhara limit and this is Avogadro's constant. Remember this. This number we famously call is as the Avogadro's constant. This is we famously call is as a Chandrasekhara limit. Now, units of time. That is what we require to understand here. So, the SI units of time is seconds, representing by small letter s. It was in 1964 when a second got defined in terms of energy change in the calcium atoms as follows. 1 second is the time interval of 9,192,631,770 periods of a specified energy change in the calcium 133 atom. This is important. You must be able to recall the atom. Like we had just seen, for calculating the atomic mass unit, we use the carbon 12 atom. For this units of time defining as a second, we use the calcium 133 atom. Atomic clocks are based on this definition. They ensure an accuracy of 1 in 10's power 11 second. Therefore, an error of 1 second only in 5000. Now the question is, as we know, the carbon 12 atom was chosen to define the standards of atomic mass unit because it was having a unique capability of 6 proton and 6 neutron. Why the calcium 133 atom was used? Actually, the calcium 133 atom was used because it was reflecting the exact radiations that we required to calculate the exact time. Okay, that's why it is being used in the atomic clocks and all, because it's having the accuracy of 1 in 10's power 11 second, and as we know, this gives the probability of you can say error, but only 1 second error in 5000. It is mostly reliable if we consider all the other options that we have. Shake, it is smallest practical unit of time. 1 shake equals to 10th power minus 8 seconds. Now, lunar month. One lunar month is the time in which the moon completes one revolution around the earth. Okay. Remember, whenever the term lunar used, actually we are comparing it with the moon. Okay. So when we say the lunar month, we are not saying that this is the mainly calendar month that we use. Okay. It is not like this. Basically, lunar month is a total time period taken by the moon to complete the one revolution around the earth. As we know, the earth revolves around the sun. Similarly, the moon revolves around the earth. So when moon starts from one point, revolves around the earth and reaches that same point from where it had started its journey, then it is considered that one revolution has been completed. And the time period, the 30 days or 27 days time period that is taken, known as the lunar month. If we go by specific, we could say the period of revolution of moon around the earth is nearly 27.3 days, ap- approximately 4 weeks. Okay. But there is another condition also. 27.3 days is the most of the time cases scenario. Sometimes it is nearly about 29.3 days also. Okay. Thus, our lunar month is of nearly 4 weeks. Okay. There is an important note. In Hindi, we follow the Vikram era or Vikram calendar. In Muslims, we follow the Hijri era or Hijri calendar. These both calendars are based on the period of revolution of the moon around the earth, which means lunar month. 27.3 days, 4 weeks exactly. Now, the concept of leap year. What do you mean by the leap year? So, a leap year is actually the year in which the month of Feb is of 29 days. Usually, if we talk about the February month, we know it is the smallest month in the year. It is of 28 days. But some years, or you can say after every 4 years, there is a year come that we call as a leap year, because on that year, the month of Feb is of 29 days, which means normal year is of 365 days, but one leap year is of 366 days because one day has been added in the Feb month. Every fourth year, as I have told you, therefore the year mensible by 4 has one day extra in the month of Feb. Therefore, the February has 29 days. And so it is the leap year that we call it. The century years, which are mensible by 400, they all will be the leap year. Examples, if we take 2000, 2400 will be a leap year. 1800, 1900, 2100, these all are the mensible by 4, but not mensible by 400. So they will not be a leap year. Remember this. We required the years that could be mensible by 400. Got it? Now, let's have a talk over the units of temperature. Okay. So generally we use the temperature to measure the hotness, coldness and neutrality of any object. Okay. Like if you say that that particular object is hot, you know that it's hot because it feels like. But if I ask you what is the intensity of its hotness, how you could tell me? If you say that this object is the cold object, and if I ask you what is the intensity of coldness in that object, how you could tell me? You required a particular standard so that you could measure the intensity of that thing, right? That is why we required a standard unit to measure the temperature. The Kelvin was adopted as the unit of temperature in the year of 1967. These are important. Okay. The Kelvin is actually the fraction 1 by 273.16 of the thermodynamic temperature of the triple point of water. Triple point of water is actually the temperature at which ice water and water vapor coexist. Okay. Like you can say These all are the forms of water. When the water cools down, it is the ice form. When the water is neutral, it is in the water form. When the water heats extremely, it is in the vapor form. So the point at which all these three forms of the water available, which means ice, water, and water vapor, then it is called as the triple point of water. Okay. Kelvin having a fixed value of 273.16 K. K is the representation of Kelvin. Now the units of electric current. Okay. So the ampere as the unit of electric current in 1948. Many times I have seen the people got confused between the electric current and electric charge. Okay. So let me clear you. Electric charge is a one particular electron that we talk about. Okay. When these kind of electrons goes through a particular system, then the flow of these electrons known as the electric current. So this is the difference. Electric charge is the constant particle or the constant electron. Electric current is a you can say moving electrons, okay, in a particular system. So ampere is the unit of electric current. Coulomb is the unit of electric charge. So do not get confused. Okay, just make this thing clear in your mind that when we're talking about static charges, these are the electric charge. But when we're talking about their movement, we are talking about the electric current. 1 ampere is the constant current, which, when maintained in each of two straight parallel conductors of infinite length and negligible cross section, held 1 meter apart in vacuum, shall produce a force per unit length of 2 into 10 power minus 7 Newton meter between them. Okay, then it is the value of 1 ampere. Now, the units of luminous intensity. Like you can say, if I ask you like how the visibility is there, how much light is there, you can say that much light, this much light. But if I ask you in the scientific term, then how you could tell me? Which means you required a particular standard so that you could measure it effectively, right? That's why we having the unit of luminous intensity too. So the candela was adopted as the unit of luminous intensity in 1979. The candela is the luminous intensity in a given direction of source that emits monochromatic radiations of frequency 540 into 10 power 12 hertz. Now it is mentioned monochromatic. Okay, remember this. Monochromatic. Monochromatic means what? Monochromatic means only the one type of light. Okay, that has a radiant intensity in that direction of 1 by 683 watt per steradian. Okay, now I just forget to tell you one thing. Let me tell you right now why the candela was adopted as the standard of luminous intensity. Actually, the candela word is straight from the candles. Because if we talk about in the historical times, we use the candle to illuminify some place, to lightning some place. Okay. So basically that's why we use the candela. Now it is the time to talk about the units of quantity of matter. Like how does we could measure the matter? Like you can say in this picture, solid having the more matter if you look carefully. Liquid less, gas is almost less. Okay. So how do we manage the units of quantity of matter? So for this, we adopted the mole as the unit of quantity of matter in the year of 1971. 1 mole is actually the amount of substance which contains as many elementary entities as there are atoms in 0.012 kg of pure carbon 12. Okay. If we talk about the two other supplementary units to measure the quantity of matter, we have teridian also known as rad. It is the unit of plane angle. 1 radian is the angle subtended at the center of a circle by an arc equal in length to the radius of the circle. If an arc length ds subtends an angle of d theta at the center of 0 of a circle of radius r, then d cos theta is equal to ds by r radian. Okay. Then the second subunit, supplementary unit we could say, is the steradian or SR. It is the unit of solid angle, therefore angle in space. 1 steradian is the solid angle subtended at the center of sphere by that surface of the sphere, which is equal in area to the square of radius of the sphere. If an area dj of spherical surface subtended a solid angle of this at the center of the sphere of radius this, then this will be the steradian. Got it? Now, move ahead. Some units retained for general use, though outside the SI or standard unit. Like here you can say name, symbol, value. Degree, liter, ton, carat, bar, curie, Roentgen, ban, RA, hectare, standard atmospheric pressure, this one. Okay. Derived units of some physical quantities, if we talk about them. So, area, m square, volume, m cube, density, kgm minus 3, speed of velocity, meter second minus 1, acceleration, meter seconds minus 2, force, kilogram meter second minus 2 or Newton or N, work energy, kilograms m square seconds minus 2 or joule or J, momentum, kilograms meter second minus 1, torque, kilogram meter second square s minus 2 or m, power, joules, s power minus 1 or watt. Similarly, like the pressure, you can see them. Frequency, that's one. Electric charge, this one. Electric potential or electromotive force, EMF, this is. Electric resistance, you can see over here. Coefficient of self-induction or coefficient of mutual induction, Henry. Magnetic flux, Weber. Magnetic induction, magnetic field, Tesla. Capacitance, Farad. Conductance, ohms minus 1 or ohms power minus 1 basically. Luminous flux, Lumen. Luminous, Lambert. Illuminance or intensity of illumination, lux or LM or Ln square. Similarly, power of lens, diopter, latent heat, this one, specific heat, gas constant, Boltzmann constant, coefficient of thermal conductivity, Wien's constant and Stephan's constant. Units of some physical quantities in different systems. Fundamental, length, mass, time. Under the centimeter, gram and second, it is cm, grams, second. Under the meter, kilogram and second, it is meter, kilogram and second. Under the feet, pounds and seconds, it is feet, reps, second. Drive, force, work or energy power, dyne, erg, second, Newton, joule, watt, poundal, feet poundals per second. Now dimensions of physical quantity. The 7 fundamental or base quantities that were chosen in SATHEE are called 7 dimensions of the physical world. They are generally denoted with the square brackets that you can see over here. Relation between some physical quantities in CGS and SI systems. Force, unit CGS dyne, SI Newton. Relation 1 equals to 10's power 5 dyne. Energy, erg, joule. Relation is 1 joule equals to 10's power 7 erg. Magnetic flux, Maxwell, Weber. Relation is 1 Weber equals to 10 power 8 max. Magnetic induction, Gauss Tesla, Weber or meter square equals to 1 Tesla equals to 10 power 4 Gauss. Magnetic intensity, Oersted or amperes meter. Relation is speed Pondels. Similarly with power, erg second, watt, and then you can see them. The Oersted symbol OE in the unit of auxiliary magnetic field H in the CGS system of units. It is equivalent to 1 dyne per Maxwell. Thus, length is represented as capital L, mass by capital M, time by capital T. Electric current by capital A, thermodynamical temperature by capital K, luminous intensity by small c and d, and amount of substance by mole. Note that using the square brackets around a quantity means that we are dealing with the dimensions of the quantity. There is another note also. The dimensions of physical quantity are the powers or exponents to which the unit of base quantities are raised to represent the derived unit of that quantity. Dimensions of some important physical quantities. For linear momentum, dimension formula is front of this. Force, okay, you can say linear momentum, this one. Force, this one. Impulse, this one. Pressure or stress, this one. Universal gravitational constant, this one. Work, energy, moment of force, this one. Power, this one. Surface tension, this one. Moment of inertia, this one. Planck's constant, this one. Latent heat, that one. Gas constant, this one. Boltzmann constant, this one. Stephan constant, this one. Magnetic flux, this one. Dielectric constant, this one. Resistance, that's one. Conductance, this one. Conductivity, this one. Electric flux, this one. Power of lens, this one. Now, we have finished the topic, not part for the summary discussion. We have talked about the mass, SI units, subunits, larger units, non-metric units. For time, we have talked about SI unit, smallest practical unit, lunar month, leap year. Temperature, we had talked about SI unit, definition, and others. Electric current, we have talked about SI unit, definition. Luminous intensity, we have talked about SI unit, definition. Quantity of matter, we had talked about SI unit, definition. Supplementary units, we have also talked about. Plane angle, we have talked about. Solid angle, we have talked about. For derived units, we had talked about various physical quantities like area, volume, density, speed, force, work, power, pressure, electric charge, and more, which having the specific SI units derived from the base units. Non-SI integrated for general use, we had talked about like degree, liter, ton, carat, bar, curie, Roentgen, man, array, hectare, standard atmospheric pressure. Dimension analysis, we have talked about like dimensions of physical quantities are expressed in terms of the 7 base quantities like length, mass, time, electric current, thermodynamic temperature, luminous intensity, and amount of substance. Conversion between systems, we had talked about. The content also provide the conversion between CGS, SI units for various physical quantities like force, energy, magnetic flux, and more. So with this, we had finished this lecture. It is requested to all of you kindly revise the facts and figures that all we have discussed in this lecture and keep yourself ready for the next lecture. With this note, let's end this lecture and thank you.